Hi all, so in today's video we're going to be looking at points of inflection, which leads on from the curve sketching notes that we took previous lesson. So one thing we haven't seen is what happens when your second derivative does equal zero when we do the second derivative test. So let's expand on that. So a point of inflection is a point on the curve where the concavity changes. It may be a stationary point, but this is not necessity. Okay. However, for a point of inflection, what we need, and there's a bit of criteria here, we need the second derivative at the point x to equal 0. That's the first thing we check. But we also need a value just before x to be substituted into the second derivative and just after x. And they must have different signs. It doesn't have to be positive and negative, it can be negative and positive as long as they have different signs. Okay, so that is the main thing there. So again, if you're watching this video, I would pause the video now and copy down those two sentences there, but that's what we need for inflection. Now we use the word concavity there because that's what actually happens to the graph. So I'm actually going to flip my slide here. So concavity happens in two directions, okay? So a curve is concave upward if the slope is increasing and the value of f dash double dash x is greater than 0, which we've seen when we do the second derivative test. F double dash of x greater than 0 means we have a minimum turning point, and you can see from these directions here, if I continue with this, I would end up with a minimum turning point regarding a positive or negative slope. A curve is concave downwards if it is the opposite, if the second derivative is less than 0, and you'd end up with a maximal point there, looking like that if it was your turning point there. Okay, so that's just a wee bit of expansion on concavity. So again, you can pause the video, copy that down, and then we can listen back. Okay, but we'll look at two examples to show more about the inflection and how we can find it. So we'll start off with the first example here. Okay, we're going to find the coordinates of the points of inflection on the curve with the equation f of x equals 2x to the power 4 minus 16x cubed plus 36x squared plus x minus 3. Okay. Now, there is an extra example in the notes, okay, that I've attached. So this is why we're doing example 2, but just for the video, this is the first example. Okay. So let's see how we would go about doing this here. So for inflection, we need to find the points where the second derivative would equal 0. Okay, so that's my first job, is to actually locate where these points are. Then what I need to do, if there is any points there, if there are inflection, I need to check just before it and after with the second derivative, do the signs change? Okay, if the signs change, then I've proven it's a point of inflection. Okay, so let's start us off here. Nice function, we need to get the second derivative. So if we get the second derivative, okay, it's going to be 8x to the power 3 minus 48x squared plus 72x plus 1. Okay, so I've differentiated that there. I want to differentiate it again. So that'll be 24x squared minus 98x. Oh, not 98x, my apologies. 96 plus 72. Okay, so I've differentiated twice in there. So now we state, a bit like when you done it higher. So at higher you always used to state stationary points occur when f dash x equals 0. We're going to do the same thing. So for a point of inflection, we need f double dash x to equal 0. Okay, so you write that statement every time you do these questions, a bit like when you've done it for higher regarding the stationary points. Okay, so we'll do that there. So let's set this equal to 0. So 24 x squared minus 96x plus 72 equals 0. Okay, you can divide every term by 24, so that you would end up with x squared minus 4x plus 3 equals 0. Okay, so again, you didn't see the 24 straight away, just keep dividing until you end up with the simplest. And then factorise that. X minus 3, x minus 1. So that will lead to two values, x equals 3 and x equals 1. Okay, so we found 2 points where we could have inflection. We don't know yet, we need to still sub in values just before and after each one here that there could be inflection here, and if there is, those would be the two x values there. Okay, so let's just check what happens at both sides. So we'll start off when, in fact, I'm going to show it a wee thing there. What would all be good practice here is, so we don't want to make x equal these values, but we're going to consider the first one x equals 1. Okay, we'll consider that first one. So I need a value just before it. So remember, we want just before it. So let's say we put 0.9 into our function, second derivative of 2. And if I put 0.9 in, I'm going to get 126 over 25. Okay, so if you substitute that in your second derivative, you would get that there. If I then put in something just after it, like 1.1, okay, sub 1.1 in, you'd end up with negative 114 over 25. Okay, so the main thing is here, the signs have changed. Okay, my first answer was positive, second answer was negative, therefore we do have a point of inflection. Okay, so what we write is change of sign. Change of concavity. So point of inflection. Okay, at now if you substitute your x value in, okay, to the original function, I'll go do this over here. So when x equals 1, substitute f1 into the original function, you would have got the answer 20. So therefore my coordinate is 120. Okay, so that is where the first point of inflection would be at. Okay. We'll now do the same for the second point. So the second value was when x was 3, so we're going to consider x equals 3. So again, just need something just before it, so we'll go 2.9. Sub 2.9 in the second derivative, you end up with negative 114 over 25. And putting something just after, like 3.1, you end up with 126 over 25. Okay, so again, signs have changed. So change of sign. Change of concavity. So point of inflection. At the value x equals 3. So again, if we come over here and work out what the y value would be, so f of 3, you substitute 3 into the original function, you would have got 54. So that would be where the second coordinate of inflection would have been. Okay, so that's the steps there. That's been proven, both these points that I found for x, where the second derivative equals 0. Because the signs change just before and after it, they do prove its inflection at that point. The only thing you need to do is just also get your y value from your coordinate there. So, very systematic, okay, just using your derivatives to help you there. We'll look at another question, okay, just to show you a different function, but we'll have a look at that just now here. So, let's have a look at this one here. I accidentally copied that one over, so let's just fix this just now. So, example 3, this is in the notes. Okay, second example of the video, but it's example 3 in the notes. Something you're asked to show. So we're going to show there is a point of inflection okay, show there's a point of inflection on the graph y equals 7x to the power of a third at x equals 0. Okay, so we're not asked to find it, they're telling us that we just need to show that there is a point of inflection there. Okay, so solution. We need to differentiate this twice. Okay, so to differentiate it the first time, I'm going to get 7 over 3 x to the power negative 2 over 3. And then if I differentiate it again, I'm going to get negative 14 over 9 x to the power minus 5 over 3. Okay, so I differentiate it twice. Now we're going to have to substitute our values in here, so we'll just tidy this expansion up. So it's going to be negative 14 over 9 x to the power 5 over 3. Okay, which would equal negative 14 over 9, and that would be the cubed root of x to the power 5. Okay, and that would be a nicer function to substitute your values into. Okay, so again, we know the value x equals 0. We need to check just what happens before and just what happens here. So at, say, negative 0.1, okay, so just before 0, the value you would get, now if you substitute into the calculator, it would approximately come out to be 72. Okay, if you turn in the calculator, it'd be a very awkward decimal, but it's very approximately 72. The main thing is positive though. Okay, that's the bit we're looking for. So we end up with something greater than 0. If I then sub in 0.1, you end up with something very similar to negative 72. Okay, but again, the main thing is it's less than 0. Okay, we get that there. So therefore, we are proving we've got a change of sign. Which means we have a change of concavity. So we have a point of inflection at x equals 0. Okay, so let's show that example as well. You all good with that?